Hello, my name is Thomas Davis. I am a XNB272 student at QUT Kelvin Grove, and I'll be presenting a biomechanical analysis of sprinting performance, focusing on the mechanics that influence maximal sprint velocity. Maximal sprint velocity is achieved by optimizing stride length and stride rate through precise biomechanical adjustments. The biomechanical goal of sprinting is to maximize horizontal velocity by generating backward-directed ground reaction forces that propel the center of mass forward. Stride length improves when braking impulse is minimized and the propulsive impulse is maximized. This is achieved by striking closer to the center of mass, applying a backward and downward force at toe-off, and maintaining a stable, slightly forward-leaning trunk. Stride rate increases with greater hip angular velocity during the swing phase, supported by knee flexion that reduces the leg's moment of inertia and it allows faster repositioning. Together, these coordinated actions minimize braking, enhance propulsive efficiency, and optimize stride mechanics to achieve maximal horizontal velocity. This deterministic model illustrates how an athlete's horizontal sprint velocity results from two key components, stride rate and stride length. On the left, the stride rate pathway shows how quickly the leg can cycle through each step. It's governed by hip angular velocity, knee flexion, and the leg's moment of inertia, factors that determine how efficiently the leg swings and repositions beneath the body. On the right, stride length is driven by propulsive forces applied to the ground. Efficient horizontal velocity depends on maximizing propulsive impulse while minimizing braking impulse, achieved by optimal foot strike underneath the center of mass, a backward directed ground reaction force, and coordinated trunk and limb alignment. Together, these two pathways balance frequency and distance per stride. Efficient sprinting therefore requires rapid limb cycling with controlled force application to maximize forward momentum and achieve peak horizontal velocity. In today's presentation, we have identified 4 key biomechanical features for both quantitative and qualitative analysis. For the quantitative variables, we have hip angular velocity and acceleration, total thigh range of motion, ground reaction forces and their horizontal and vertical components, plus their impulses, trunk lean, and center of mass distance to foot. For the qualitative variables, we have hip flexion and retraction timing, trunk lean and alignment at contact, foot strike pattern and ground contact orientation, and thigh shank foot coordination. The observation strategy and setup used in this analysis included the sprint trial being recorded on an outdoor track using a smartphone camera at 240 frames per second. Reflective joint markers were placed at the greater trochanter, lateral knee, lateral malleolus, shoulder, and elbow. A 1 meter ruler was used for calibration within the Canovia software to ensure accurate distance and angle scaling. The background was a high contrast white wall to facilitate marker tracking. The athlete performed 3 familiarization runs with approximately 1 minute of rest between each to reduce variability and achieve consistent performance before his maximal sprint. The following calculations were derived from video analysis to be used for the quantitative analysis portion of this presentation. Please pause here to view the calculations and formulas used. The athlete's total thigh range of motion was measured at 92.7 degrees, which is lower than both team sport and elite sprinting athletes' normative values recorded by Clark et al. In 2025. They found around 98 degrees for team sport athletes and about 105 degrees for sprinters. This reduced range indicates that the athlete isn't driving the thigh as far forward or backward during the swing phase, limiting both hip extension and stride length. In practice, improving this range could enhance frontside mechanics, stride efficiency, and overall sprint performance. The ground reaction force of the runner was 514.63 newtons. The ground reaction force was also used to determine the horizontal and vertical ground reaction force components and their impulses. The horizontal ground reaction force was measured at 464 newtons, and the vertical ground reaction force was measured to be 225.6 newtons, with a ground contact time of 0.09 seconds. The horizontal impulse was measured at 42.2 newtons by second, and the vertical impulse was measured at 20.5 newtons by second. The relatively high horizontal impulse indicates strong propulsive capacity, while the moderate vertical impulse supports flight time. However, the 26-degree center of mass foot angle suggests overstriding, increasing braking impulse before propulsion begins. Average hip angular acceleration of the runner during the swing phase was determined by converting the angular velocity into radians per second. It was determined to be 11.58 radians per second squared. The moment of inertia of the leg about the hip of the runner during the swing phase was determined to be 2.55 kilograms by meter squared. The torque of the hip during the swing phase was determined by the product of the moment of inertia and angular acceleration, which derived 30.5 newtons by meter. The athlete's hip torque demand aligns with the levels typically required during mid-swing phase acceleration and elite sprinting, according to Cross and colleagues in 2022. However, a greater trunk lean of 19.8 degrees increases the torque demand on the hip flexors to maintain limb acceleration. Excessive trunk lean also shifts the center of mass forward, delaying hip retraction and reducing the ability to align the ground reaction force vector beneath the center of mass. In summary, the runner shows high angular velocity during the swing phase due to rapid leg repositioning. However, at foot strike, the foot lands 26 degrees ahead of the center of mass, and the knee is nearly extended, increasing the moment of inertia, mainly because the lower leg contributes 87% of the total leg inertia in this position, according to Dempster in 1955. The runner also has a trunk lean of 19.8 degrees, which is much greater than that is seen in elite sprinters. Their total thigh range of motion is 92.7 degrees, relatively low according to Clark and colleagues in 2025, suggesting limited hip extension and reduced stride efficiency. Overall, the runner generates fast leg movement over a small range, indicating rapid but mechanically inefficient motion, with heel striking, forward foot placement, and excessive trunk lean contributing to suboptimal technique. Qualitative analysis portion of this assessment, I evaluated the joint positions of the runner during his sprint. During the swing phase, the athlete demonstrated pronounced hip flexion, with the thigh moving well ahead of the trunk. The posterior motion of the thigh was delayed until after touchdown, indicating a suboptimal swing to stance transition, as described by Clark and colleagues in 2025. At foot strike, the athlete made contact with the rear foot strike pattern, and the knee nearly extended, placing the foot well ahead of the center of mass. This forward foot placement reflects an overstriding pattern, which typically increases braking forces and reduces running efficiency, according to Clark and colleagues in 2025. The athlete's chest was positioned forward over the knees at the initial stages of the stance phase, indicating greater trunk lean than typically seen in elite sprinters, according to Nagahara and colleagues in 2024. This excessive forward lean limits the hip's ability to retract effectively and prevents the leg from striking directly beneath the center of mass, further contributing to braking. Such positioning also restricts hip extension torque generation, ultimately constraining stride length and forward propulsion, according to Clark and Ryan in 2022. The recommendations and technical cueing that I would give to improve sprint efficiency for this runner would be to drive the knees up to hip parallel, in order to increase thigh range of motion and enhance front side mechanics, to improve hip angular velocity during the swing phase, but also promote greater hip extension torque at toe-off, ultimately supporting longer, more forceful strides and improved sprint velocity. The next cue would be to strike back beneath the hips to encourage hip retraction at contact and apply a downward and backward force at touchdown, which reduces braking impulse and center of mass to foot angle at touchdown. The next cue would be to maintain a tall posture to minimize excessive trunk lean and reduce anterior pelvic tilt, which minimizes hip extension torque. And finally, I would also encourage a forefoot strike pattern to improve elastic recoil and reduce braking duration. In conclusion, the analysis revealed clear evidence of overstriding, resulting in increased braking impulses. We also observed limited hip retraction and a suboptimal foot strike pattern, both of which contribute to inefficient sprint mechanics. To address these issues, the athlete should focus on optimizing postural alignment to enhance stride length by leveraging their hip extensors to improve propulsion and refining front side mechanics to increase stride rate and reduce braking. Together, these adjustments are expected to decrease braking impulse, improve stride frequency and length, and ultimately enhance horizontal sprint velocity.